I'd now like to turn our attention to heat engines, which are devices that can take some heat that's being transferred through a system and extract useful work. So to that end, since we're going to be thinking about useful work, the first thing we'll be doing is defining the work done by the system. So we'll go ahead and call that W sub S, and that's just the negative of the work done on the system. So our first law of thermodynamics, which we've been writing as delta E therm equals Q plus W. We can also express it if where this is the work being done on the system. We can also write it as delta E thermal equals Q minus the work done by the system. And for this treatment here, where we're thinking about heat engines, where we're extracting work to have the system do work on something else, this will be a more useful focus. So what this will mean for our PV diagrams is say this is my initial state, that's my final state, and we connect it with some thermodynamic process. We saw that the magnitude of the work done was equal to the area under the curve. Now, before, when we were talking about the work being done on the system, we said that left to right was negative and right to left is positive. So here, the work done by the system will be positive if we're going from left to right in a PV diagram, and the work done by the system will be negative if we're going from right to left in a PV diagram. And this makes sense. If we're going from left to right, it means the volume of the piston is increasing. So that's our power stroke. So we're pushing against the external load. And also, in order to really be thinking about heat engines, we'll also need to introduce a thing called an energy transfer diagram. I alluded to these a little bit earlier, but didn't get into detail. Here it's worth getting into detail. So whenever we're thinking about heat engines, or refrigerators for that matter, we'll show how to modify the diagram if it's a refrigerator later. The idea is always going to be that you are transferring heat out from some hot reservoir. And we usually indicate this outward extraction of heat with a double-lined arrow. And the amount of heat we'll pull out is Q hot. And then we'll go through the heat engine itself, which will contain what gets called the working substance. And this is so we can be as generic as possible. It's a really lame name, I know. The idea of the working substance, most of the time this is going to be a gas, and we're going to be doing work expanding a piston. However, you can have things like piezoelectric systems, for instance, that if you heat them up, you change their electrical properties in a way that they actually create a little bit of an electrical current. And so we're extracting some work out from the heat transfer through this piezoelectric crystal. And so we can't just say it's a gas, because we've got weird things like these piezoelectric crystals. So anyway, in normal operation, we will be extracting work out from the working substance and rejecting some amount of heat to the cold reservoir. And the hot and cold reservoirs are just simply thermodynamic systems such that any typical amount of heat being transferred in or out isn't going to change the temperature to any amount that we care about. For instance, we could imagine the cold reservoir being a glass of ice water. As heat goes in, you melt the ice cubes, but you keep the temperature at 0 degrees C. Or we could just imagine it being, say, an Olympic-sized swimming pool. And sure, technically you raise the temperature of the Olympic-sized swimming pool when you transfer in a little bit of heat, but not by much. And so for what we're thinking of, we'll just approximate as not changing it at all. So to give one example of this, we could imagine just, say, having something like a copper bar. So on one end, we can have a Bunsen burner running, like so, at some temperature T hot. And on the other end of my copper bar, I've got a block of ice that I'm melting. And so we're maintaining that at T cold. If I were to write draw an energy transfer diagram for this, it would look like this: T hot, working substance, T cold. You always draw these. And we will extract Q hot from the hot reservoir and reject Q cold to the cold reservoir. And in this case, there would be no work being put into or extracted out from the system. So we would observe in this case that Q hot equals Q cold in order for the first law of thermodynamics to work. Now, just a quick note, not every energy transfer diagram that you can draw is one that can actually happen. So let me just draw a couple that don't actually happen, and we'll get into the whys for those. So I could imagine drawing the reverse situation for my copper bar. So T hot, T cold. There's my copper bar, the working substance. But instead of extracting heat from the hot reservoir and rejecting it to the cold, I extract it from the cold and reject it to the hot with no input of work. Now, in an earlier video, I alluded that this is actually violates the second law of thermodynamics. So just because we can draw it doesn't mean it happens. Another one that it'll turn out that also violates the second law of thermodynamics would be if we could have some device that perfectly turns heat into work. We'll be showing why you can't do that in the next video. But you would draw it something like this: our working substance here. So Q hot, work done by the system going out like that. Nothing rejected to Q cold. This also turns out to violate the second law of thermodynamics. You will have to reject a certain minimum amount of heat to the cold reservoir in order to comply with the second law. So for a typical heat here's an example of one that does work, but is weird. See if you can figure out what it is. So I got a hot reservoir, working substance, cold reservoir. Hot reservoir, cold reservoir, working substance. We input work, and reject it all to the cold reservoir. You've seen this before. What is it? Pause the video and get back with me. It turns out this one's Joule's experiment. Where he used a paddle wheel to do work on water. The water is the cold reservoir. So all the work got converted into heat that got rejected to the cold reservoir, in this case, the beaker of water. All right, that's all well and good, but usually we're interested in heat engines that can actually run repeatedly. So typically they're going to run in some sort of a cycle. So then we'll get the more standard T hot, T cold, Q hot, Q cold, and we're hoping to extract work out from the system. So when we're running a cycle, we're going to do positive work. So we're going to get positive work out during the compression, during the expansion stroke, and then during the power stroke, and then there'll be a compression stroke later where we'll have to do work on the system. But the idea is we'll do less work to reset it than we will to push back out, so you'll gain something from it. So over one cycle, by the first law of thermodynamics, remember delta E thermal equals Q minus work done by the system. For over one cycle, the change in the thermal energy has to be 0. And that was, remember, because you end up back where you started from. In order to end up back where you started from, you also have to end up back at the same temperature. And since the temperature we've now seen is directly proportional to the thermal energy, this means that over a complete cycle, the change in the thermal energy is 0. So the work done by the system will equal the net heat transfer into the working substance. But that's going to be what we get in from the hot reservoir minus what we reject to the cold reservoir. Now, what you're typically going to be interested in is, okay, how efficient can this process be? And any figure of merit in physics gets defined in this sort of a way. So one of the usual symbols for efficiency is eta. If you write that in English, you'd say ETA. And just again, to pull out the special paper that we used in second grade, you draw an eta like this. So think of it like an English N with a really long hooky tail thing at the end. This is a different E kind of sound in Greek from the one that's made by epsilon. Anyway, any efficiency, or for that matter, any figure of merit, so like a coefficient of performance, anything like that, gets generically defined as what you get over what you had to pay. So in this case here, if we're talking about what we're going to get out from a heat engine, well, what are we getting? We're getting the work done by the system. What do we have to pay to get that? Well, typically, in order to maintain the hot reservoir, you're burning fuel, or you're bringing in electricity, or something like that. And so what you had to pay for, often quite literally, is for the heat transferred from the hot reservoir. So the heat rejected to the cold reservoir is just a loss, but our efficiency will be the work we get out of the heat of a cycle of the heat engine over what we extracted, the heat we extracted from the hot reservoir in a cycle. Okay. Now, we can think about, so let's just have a nice example of how such a process might work. So we can imagine, say, we burn a Bunsen burner. Like so. And the idea, so our working substance is going to be the gas in here. So here's our piston, and the practical work we want to get out is going to be lifting some mass. Okay, well, we can just let this go. As we keep heating this up from the Bunsen burner, the gas is going to expand. Like so. So this process that we have here is going to be an isobaric expansion. And this is because since we're exposed to air all the time and we've got this weight on here that hasn't changed, the pressure doesn't change anywhere along the way. So this is a constant pressure process. Then in the next step, we imagine putting in, we'll turn off the heat. And at the same time we turn off the heat, we'll stick in a locking pin. And we will remove our lifted mass, like so. All right, and then we're just going to let this whole thing cool down to room temperature. So this process here is going to be a isochoric cooling. And then finally we can imagine that in our last step here, we go ahead and have some external force push the piston down, and we do it slowly enough that it remains exposed to air. So then this will be still at room temperature. This will be an isothermal compression. So just some external forces doing that. And then we can imagine sticking our mass back on and doing this all again. All right. Or, well, actually it would be a new mass, because the idea is the useful work is we keep lifting masses. Let's draw a PV diagram for this and think about where the heat flows are and what the work is that we get out of this. So plotting P versus V. So in my first step here, so I'll just label this 1 to 2, like this. This is my isobaric expansion. And then this bit here where I'm just cooling down to end up here at room temperature, this is going to give me my isochoric cooling constant volume. Like so. And then finally, we return along an isotherm. So this will be my that didn't look too good. There we go. So this would be my isothermal compression. So my cycle will be going 1 to 2 to 3. Now, in the first step, from 1 to 2, the isobaric expansion, we added heat by burning the Bunsen burner. So we bring heat in from the hot reservoir. Now, in the isochoric cooling part of this process, we're just letting it sit there and let heat drift off to the cold reservoir, like so. So in this step, we're losing heat to the cold reservoir, but we're not done yet. Once we get this down to our new lower temperature, back at room temperature again, when we do work on this, we're going to be increasing the thermal energy. We're going to be increasing the thermal. Since we're doing work on this, by the first law, delta E thermal will equal Q minus WS. Now here, delta E thermal is 0 because we're keeping a constant temperature. So not for the same reason as before where we said it was a cycle, but this is just because it's isothermal. And the work being done by the system here is negative. So minus a minus is a plus. So that means that the heat being transferred in is negative, which means it's actually an outbound flow. So as we do work compressing the gas, we heat the gas up, but we're doing it slowly enough so that it stays in thermal equilibrium with the environment, which in order to do that, that excess energy has to be transferred out to the environment. So in this step 1 to 2, we are extracting heat from the hot reservoir, and then in the 2 to 3 and the 3 to 1 legs, we're rejecting heat to the cold reservoir. Now, I can't imagine of a practical application for this particular engine, but I chose it because it's instructive. Now, what's going to be the difference in the heat is going to, in the Q hot and Q cold, is going to be the useful work that we extract from this. So this, the area enclosed by the figure, that's the work we get out. Now, here, this is the opposite of what we were having before when we were thinking of work being done on the system. Since this is work being done by the system, it'll be positive here because it's going clockwise. If we're going counterclockwise, it would be negative. So if you think about a clockwise thing, means that you're doing some sort of an expansion. So you've got a power stroke, and then you go ahead and do a compression stroke. And the idea here is we're going to be extracting out more heat from the hot reservoir during the expansion process than we do during the compressions. Okay. While we're at it here, let's talk about thermodynamic refrigerators. So from a thermodynamic perspective, all a refrigerator is a heat engine run backwards. So you input work, and then you can move heat from the cold reservoir to the hot reservoir. Now you reject more heat to the hot reservoir than you extracted from the cold, because in order for the first law of thermodynamics to be satisfied, the work being done has to be equal to the Q cold plus the work has to be Q hot in order for the total heat transfer to equal the work. So usually with the refrigerator, our figure of merit is the thing that gets called the coefficient of performance. And again, following our idea of what you get over what you had to pay. here, what you get is the heat being extracted from the cold reservoir. If this is your actual refrigerator in your house, this is the heat being extracted from your leftover sandwich in order to help keep it chilled down. What you had to pay, in this case quite literally, is the work that's being done on the system, being input into the system. In this case here, it's electricity is being used to turn a motor. And in a typical refrigerator, you'll go through you'll run a compressor that compresses down a gas. You go ahead and vent both the heat you extracted from a cold reservoir plus the extra heat that you got from doing work on the gas to compress it through the panels through the grill on the back of the fridge. And then you go ahead and let the gas inside the refrigerator, you go ahead and let the gas expand. And in order to do that, it extracts heat from the interior of the refrigerator. So Q cold is what's being pulled out from the sandwich. Q hot is what's going into the surrounding environment. And the work is is coming from the motor that's being run by the electricity that you're getting from the wall. So usually we could use eta here, but a lot of people use a capital K just for K for coefficient misspelled, just to keep it distinct from a thermodynamic efficiency. Alrighty. So in the next one here, we will be taking our heat engines and thinking about what the limits are from the second law of thermodynamics. So we'll see that we can't be too efficient, but we can't. But there's a limit to how much work we can get out of a heat engine, and there's a limit to how much heat we can extract from a cold reservoir in a refrigerator. So we'll see you in the next video.